All right, here we go. Let's take a look at the first derivative test. So we're going to use the first derivative to graph some functions here. So before we get into that, I actually graphed one for you. So I hooked you up here. Here's the function. This is my f of x. And I want to talk about critical points again. Remember, that's when the slope of the tangent line is 0. Something like, ooh, look at that straight line. That's nice. Like right there. So a critical point would be like at, let's say, 3. If my pen works, there we go. Where else is the slope of the tangent line 0? It's also here. That's more like it. That's my normal line right there. And that's going to be when x is 5. Or when the slope is undefined. So this isn't, we can't take the derivative here if it's undifferentiable. So at 6. So I've got these critical points here. So it also could have been a vertical horizontal, but this is just undefined right here. So if you can't take the derivative or the slope is 0, that's going to cause these critical points. What's happening at the critical points? Well, these are these max and minimum points going on right here. So we're going to break these into what we call these sign charts, and we're going to look at the intervals and specifically what's going on with the derivative. So if I look at, when x is from negative infinity to 3, if I look at this first interval here, what can you tell me about the graph? Well, what is the slope of the tangent line of every point in here? That's right, it's positive. All these are positive. It's getting less positive, it's kind of flattening out until it is 0. But right here, the slope is always going to be positive here. So it's a positive line, or positive derivative. What about from 3 to 5? So the next interval from here to here, well, what's the slope of the tangent line? It is always going to be negative. So this is negative. And how about from 5 to 6? It goes back up to the slope of the tangent line is positive. Ooh, this is rough looking handwriting there. And then from 6 on right here, the slope of the tangent line is always what? Is always negative. So what we're going to do is we're going to look at the derivative to find these changes from positive to negative. So if it goes from an increasing function to a decreasing function, what does that create right there? Well, yeah, it's going to create a maximum. So we're going to use this to locate maximum. If it goes from a negative to a positive slope, what's that creating? It creates a minimum. And if I go from a positive to negative, so I can see, yeah, these are max and min points. Now in the pictures right here, it's easy to see, oh yeah, there's the max, there's the min, there's the max. But we're going to start taking these critical points and labeling them as, sure, this was my max, this was a max, this was a max, and in the middle was a minimum. Excellent. So this is going to help us sketch some functions here. Let's try it. So let's sketch this bad boy here. And in fact, this is the nice sign chart that I want to fill out here. So I kind of drew this one for you, kind of hooked you up. So first thing we need to do is always find these critical points. If I want to sketch this curve, I got to find the derivative. What is the derivative? Well, this is just a straight power rule. So this will be 3x squared. Bring down the 2 on that will give me 3x, and the constant disappears. And to find the critical points, I set it equal to 0. Let's factor this bad boy, and I can take a 3x out, and I'm left with what? I think that's x minus 1. So what are my critical points? It's going to be what causes this to be 0 is 0. What causes this side to be 0 is 1. So once I factor it, these are my critical points. So essentially, like, this is my critical points are at 0 and 1. So I need the interval to the left of this. So what is to the left? Well, it goes from negative infinity to 0. Then what's it doing? It's going from 0 to 1. And then 1 to infinity. So here are the intervals that I'm going to check for my derivative. So I know that there's something going on. Here are my critical points. So I got my critical points. Are they maxes? Are they mins? Are they nothing? I don't know. We got to figure it out right here. So what do? Once we set up, these are my critical points I'm going to check. I'm going to test some points. So you got to think of a number. What's the number between negative infinity and 0? I mean, you could choose negative 470, but I'm going to choose negative 1 because 1's so easy to work with. A number between 0 and 1/2 would be, between 0 and 1, I'm going to pick a half. And then what's a number between 1 and infinity? Let's just do 2, keep it simple here. So what's the idea here? We want to know, well, what is the value of the derivative? So you actually got to plug this in. When I put negative 1 into the derivative, what do I get? Well, if I put negative 1 back into this derivative, and what's going to happen here if I go 3 times negative 1 squared minus 3 times negative 1? And all I'm really concerned about is the sign. So this is really going to be 3 plus 3. It's 6. But what do I care about? That is a positive. So what do I get from a positive derivative? So important here. My conclusion is that the function is increasing. It is going uphill. Excellent. So I'm not going to be able to use a graphing calculator and just put this bad boy in here. This was hugely important before graphing calculators could do that for people. So I know the function's increasing on this interval. Now we got to do it again. Let's go ahead and plug in what is the derivative at 1/2. And again, I'm really just concerned about that sign. When I put 1/2 into the derivative for x, I'm most concerned, is it positive or negative? So that's going to be 3/4 minus what? 3/2. So if you get a common denominator here, let's just finish it out. That'll be 6/4. So when I subtract them, I get minus 2/4. But again, so the derivative at what? 1/2. The thing I care about is negative, and it is negative 1/2. Negative derivative means what? It means my function is decreasing. Awesome. How about when I put 2 into there? I'm kind of run out of room. Let's do the derivative of 2. And if I put 2 into this bad boy, wherever there's an x, and I'm going to get, what is that, 12 minus 6, but that's going to be positive, so that's awesome. So it's a positive 6, and what does that tell me? It's increasing. So from looking at this table here, what's going to happen? I've got an increasing function, then it decreases, so that's going to create my maximum. Then it's decreasing to increasing. This is a minimum if it goes decreasing. So we're looking for, when does it change? When does the derivative change from a negative to a positive or a positive to a negative? Can I make a rough sketch of this thing? Sure. I know the general idea what's going to happen. It's going to increase, decrease, then increase. Maybe you want to get some points in here. A lot of times it's fun to find, but you can find the x-intercept pretty easily, you know, or the y-intercept. Let's do y-intercept. When x is 0, what is y? So if I put 0 in here, 0 minus 0 plus 2, well, that worked out well. I know it's going to cross right here, so I at least know this is going on. I know there's some action. Well, that is true. What is this? 0 point? We didn't even label it. That's the maximum. So I know that's a maximum point right there at 0. I know this is a minimum point at 1. So maybe I want to plug 1 in here if I want to get some more values. So let's plug that into the function. What is the f of 1? And again, we're not going to go too, I'm going to make a rough sketch of this. So I've put 1 in, it looks something like this. We're not going to go too crazy. So it's like 3 minus 1.5. So at 1, I'm going to be at 1.5. So it looks something like this. So it's an increasing function. So I'm guessing that it does something like this. It's increasing, hits this, comes down, hits this, and goes back up. So that is a general rough sketch of this thing. I could go on and maybe find the x-intercept if I was supercharged to do that, but I think I hit the general idea: increasing, decreasing, increasing, max, mins, whatnot. Nailed it.
All right, here we go. Let's take a look at the next one. So I know some of you out there are probably thinking, oh, great, curve sketching. Very impressive, Mr. Bruss. Like, I have a graphing calculator. It can sketch some curves pretty well. Yeah, that's true. Like, graphing calculator, you can just plug them in. But looking, figuring out what's going on in the graph can help you in other situations. So let's use this whole idea of derivative to talk about this particle motion thing. So you got this particle going left and right on the x-axis. Describe its motion. So I'm actually going to use one of those sign charts to describe the motion. So if I want to describe the motion, there's a position function. Let's go ahead and find the velocity, or the first derivative here. Oh, dang it, I gave us a little quotient rule. What do you mean, dang it? I love it. I love quotient rule all day. So what do we got to do here? We got to do a little u prime v minus uv prime all over v squared. So if we plug this bad boy in here, u prime is just going to be 8 times that by the v, which will be t squared plus 1. And then we're going to do a little minus the u, which is the first part, the 8t, all over v prime. V prime is 2t, the derivative of the bottom there. All that's going to be over v squared. So the bottom squared, and a lot of times I don't like to write that out. I'm just going to go ahead and plug it just like this. So we probably want to clean this up a little bit. Why do I want the derivative? Well, that's going to tell me what's going on. And probably most important, let's clean it up here and see what happens. If I distribute my 8, I'm going to get 8t squared plus 8. That's a terrible looking plus sign. Let me try that again. 8t squared plus 8. Multiply those out, minus 16t squared all over that bad boy on bottom. And that thing's squared. And then combine like terms here, and I'm looking at what? I'm looking at 8 minus 8t squared all over t squared plus 1 squared. So there is the derivative right there. Awesome. So now I have the derivative. Well, why do I need this derivative? So I want to know, when is the velocity 0? When is this thing not moving? And then I'm going to, from there, be able to say, is it increasing, decreasing, things like that. So it's the same thing we were just doing as for finding max and mins. we're going to use these max and mins, but now it's going to say it's not moving. It has a velocity of 0. So when I do something like this, I don't really need the bottom. If it's a fraction, if the top equals 0, 0 divided by anything is 0. I check the bottom for excluded values, but that'll never be 0 on the bottom, so I don't have to worry about that. So really, all I got to do is say, hey, when will this equal 0? And this is an equation we can solve. You can just subtract 8 from both sides. You get negative 8t squared equals negative 8. So t squared equals 1. So what is t going to be in this case? Well, we are going to have some critical points at plus or minus 1. If you square root both sides there, you get the plus or minus 1. So I want to use the sign chart table with these critical values here and see what I get. So my first thing was the intervals. And what are my intervals? Well, I've got an issue at negative 1, and I've got an issue at 1. So when I do these tables, I'm going to do, this is going to be from negative infinity to negative 1. This is going to be from negative 1 to 1. And this is going to be from 1 to infinity. So a lot of times in these motion problems, we'll say time is greater than 0, but I didn't specify because I really just enjoy this table, so I want to have more on there. So then what we can do, we're going to have our test value. So we can test a value in this thing. So maybe I want to test negative 2. Great one to test is 0, so super easy. And then maybe I'll do positive 2 over here. And what am I doing? I'm going to plug that into the derivative. Once I have that bad boy, I can come up with a conclusion. So when I'm describing the motion, I want to know, is it going left or right or not moving, are really my only options here. So let's plug these bad boys in here. I want to know what is the derivative at negative 2 here. So this first case, I'm just looking at is it positive or negative. That's all I care about. So you can put it in any, they're all the same. So I think that was our most simplified one right here. Is this our most simplified derivative? It looks like it. So I'm going to put negative 2 in there, and I'm really just most concerned about, is it going to be a positive number or negative number? So this looks kind of cray-cray here, but that's all right. Plug in negative 2. We got to clean this up a little bit. So on top, we're going to have 8 minus, this will be 4, so it'll be minus 32. So what is 8 minus 32? That should give me a minus 24 on top. And then here, I'm going to say negative 2 squared is 4 plus 1 is 5, square it in 25. So I'm going to say the f prime of negative 2 is a negative number. It equals negative 24 over 25. But the most important thing here is negative. So if it's negative, I would say it's a decreasing function. But in this case, what does that mean? It's moving left. So because it's negative, it's moving left. So the same idea we were just doing, but now I'm talking about motion. What's happening at negative 1? Well, it's not moving. That's a critical point, so it's not moving. So you could even say that instead of max or mins, we can say it's not moving. What happens when I plug 0 into this? 0 is such a great one to plug in. So if I plug in 0 for all my times here, this will be 8 times 0. On bottom, I'm going to have 0 squared plus 1 and then square it. So that whole 0 thing is gone. It's just going to be 8 over 1, which is just 8. So the f prime of 0 is 8, but the most thing I'm worried about, it's positive. So since this is positive, what's happening? In conclusion, it's moving right. And then I can put in a positive 2. So what is the derivative at 2? It's going to be the same thing, isn't it? It looks like all my t's are squared here in my derivative. So if they're squared, let's do this. And we're going to put our 2 squared plus 1 all squared. So it's still going to be the same thing, negative 24 over 25, because if you square those negatives, they become positive. So again, I have the f prime of 2 is negative 24 over 25, and the thing for that is it's moving in the negative direction or it's moving left. So there we describe the motion. You're more than welcome to say, hey, at t equals 1 and negative 1, it is not moving. That would be some good descriptions to add there. If this was not a particle motion problem, I could have just said, hey, find the max and min. So if it goes from a negative to a positive, back to a negative, and these different things. So what's happening? I'm going negative to a positive is a minimum. Then I got a maximum when I switch back at the 1 there. So it's the same kind of thing, but now I'm talking particle motion. All right, exciting. Very nice. So a lot of times I just want to say, hey, I don't care about the increasing, decreasing. I just want to know where the max and min. So I just need to find the max and min. So we're actually going to use the first derivative test. This is a test we're going to use to find it. So next section will be second derivative test. You're going to have some options. You don't have options in this one. You just are going to have to do first derivative test. So if I'm just looking for any kind of extreme, any kind of max or min, you always find the derivative. We want to know, when does derivative equal 0, or is it undefined? So if I take the derivative, we get a little chain rule action here. So you do derivative of the outside, rewrite the inside, drop that power, negative 1/3. And then what's the derivative of the inside? It looks like it's going to be 2x. So let's clean this up a little bit here so I can work with it. Nothing really seems to cancel, so on top I'll have 2 and 2x is 4x. On bottom, I'm going to have 3 times. The negative moves it to the bottom. So this is the cube root of x squared minus 4. So this is pretty crazy here. There's my derivative. So I want to know any possible critical points will be when this equals 0 or it's undefined. Well, check it out before I even solve it. This could be undefined in this case. Why? Because if you cannot divide by 0. So you're really thinking, hey, when does this bottom right here, when would this ever equal 0? It is not allowed to equal 0, or else I have it undefined. Well, in this case, if this was 0 in the square root, or I'm sorry, cube root of 0 is 0, 3 times 0 is 0, so I can't have this be 0. So you can solve this mathematically if you want, but it's going to be 2 or negative 2. Let's solve it, though. Let's say you didn't know that. You could divide by 3. They cancel. How do you undo a cube root? Well, you cube it. So 0 divided by 3 is 3. Then you cube it. You still got 0. So now you're finally at x squared minus 4. Add 4 to both sides. You get x squared equals 4. So you're going to get x equals the square root of that plus or minus 2. So those are where it's undefined. So they're actually critical points. We have to check these things. Where's the other part? Well, it's a fraction. So when does the top equal 0? Well, that's an easy one to solve. When does 4x equal 0? We'll divide by 4. It's when x is 0. So here are my critical points right here. I'm not going to make the sign chart here. You're more willing to make the sign chart. It just it really justifies it. It really brings it home. But if you want to just use the first derivative test, all you have to do is take these points. And even if I'm going to sketch something somewhat maybe informal, like here's 0, negative 2. Here are my critical points. I still need to know what's going on with the derivative. So this is not enough here. But I got to say what's going on. Is it changing signs? That's what I'm looking for. Does it go from increasing to decreasing or vice versa? So I'm still going to have to look at the derivative. And I'm going to have to check some points like negative 3. It's like what's happening over here. So if I put negative 3 into this function, these are crazy functions here. I'm sorry, in this derivative. So if I put in this derivative, what is the f prime of negative 3? So I put negative 3 in there. I'm going to have 4 times negative 3 all over 3 times the cube root of negative 3 squared minus 4. So I'm really looking for what is the sign here. So I'm going to have a negative on top. Square this, I'm going to get 9. 9 minus 4 is 5. So it's terrible looking, isn't it? That is it. Oh my goodness. I made that one great. So you've got negative 12 over 3 times the cube root of 5. Is this positive or negative? It is definitely negative. So if I can come up here and say, hey, I know that this is a negative number. So even though I don't have a calculator, I don't know what that weird decimal is. Doesn't matter. I know it's negative. So the function is what? Over here, it's decreasing. It's a negative. Okay, let's check the next interval here. So between negative 2 and 0 is going to be negative 1. So I'm going to do the same exact thing. Plug negative 1 into my derivative and see what I get here. So wherever there's an x, put in negative 1. So I'm going to have cube root negative 1 squared minus 4. And again, I'm just looking for what's it going to be, positive or negative. So on top is going to be a negative. On bottom, negative 1 squared is 1, minus 4 is negative 3. So don't freak out. Sometimes people freak out when they get that negative. It's in a cube root. Totally cool. If you have a cube root of a negative, it's going to be a negative. So this is going to be a negative. And you could actually pull that negative out if you want in front. But it's going to be a negative over negative. This is actually a positive number. So if you want to pull that, we can pull that number out. See what will happen here is you can say this is the same thing because it's going to be a negative cube root, and then these cancel. So this number is positive. That's the main goal here, is you got a positive number. So you got to show that it's a positive number, and now I know the function's increasing here. So boom, I've got an answer at negative 2. It was a decreasing function. It goes to increasing. So this is very, very informal, but as long as you have this is the justification right here. This is justifying what's happening. So if I want to use the first derivative test, boom, I need to first identify critical points. So I identified -2. Then I took a point to the left and to the right and showed that it changed sign. So here is a sentence that you are going to love to hate right here. Okay, so here we go. We're going to justify this thing right here. So here's a sentence, and it's a little template we're going to use here to justify. So using the first derivative test, we showed it there. Now we have to write this out. I know it's kind of a pain, but we're going to write this sentence so much we're going to be pros at it. So what I just showed there, I showed at -2, we have what? It goes from decreasing to increasing, so we have a minimum. So you have to write this out. There's a relative minimum at what? At x equals -2. Because, how do I know? Because the derivative changed from negative to positive. So you're going to have to somehow have all this information. That's just to prove one thing. So you're going to have to come up here and show that to the left it's negative, to the right it's positive in my derivative. Then you have to write that out. Well, it's got to be a minimum because it goes from a negative to a positive. Wow, that seems like a lot. Yes, it is. So that's why that big fancy sign table is nice. You don't have to use it. But you need to show these key points here. So if you prefer the sign chart, use it every single time. If you don't want to use it, you can use this bad boy here. Now let's finish it out. In fact, why don't you try to finish it out? So we're going to have something happen at 0. Try to determine if there's anything going on at 0 or if there's anything going at 2 and justify it. See if you can justify it and write out your own sentence for 0 and 2. Good luck on that. All right, here we go. So I went ahead and found what happened between 0 and 2. So I put in 1. The derivative of 1 is negative, so it's a decreasing function in between. And then what's happening after 2? I picked a 0.3, but it doesn't matter. Any point after 2 is cool. And I got a positive. So here is a very rough sign chart. This would not count for anything on its own, just this piece. But when you add what's actually happening here, this is cool. Now we've actually shown it. So then I took all that information, and I realized it was decreasing to increasing to decreasing to increasing. So that made a relative maximum at 0. It was going from positive to negative. And then it's a relative minimum at 2 because it goes from negative to positive. That's how you use a first derivative test. I know it's tedious, but to get all your points and to make sure you're cool, write that bad boy out. You got to have all that information. So if you like the big formal sign chart, use it. You can kind of get away with that as long as you have all those derivatives evaluated in there. Awesome. Let's just see the picture of that. So if you have your graphing calculator, you can check and see here it is. This is actually the function x squared minus 4 to the 2/3. You can see what's happening here. And here are my minimums, and there's my maximum right there. So I thought you'd want to see the calculator. Pretty cool. All right, moving on. I know what you're thinking, oh man, I'd love to see this with some trig functions. They have lots of max and min. So we're usually going to limit them to a certain interval, and maybe I just want to know where a function's increasing or decreasing. So if you just need to show this, again, you can make your nice sign chart, but the key to anytime increasing, decreasing, or max or min, we got to find the derivative. So this derivative is just 1/2, and then what's the derivative of sine? It is cosine. So there we go here. I did want to show you this because I wanted to just say, okay, now let's set it equal to 0. Let's find these critical points. So we can solve this equation. Sure, no problem. If you subtract a half from both sides, boom, they're gone. So we've got negative cosine x equals negative 1/2, and you can divide by -1 here, so you got cosine x equals positive 1/2. And then where does that happen? Where does cosine equal 1/2 around your table here? Well, it should happen when x is pi over 3. In the first quadrant here, it's pi over 3. Where else is cosine positive? Should be down here in that quadrant, the fourth quadrant. So that should be what? That should be 5 pi over 3. So those are the 2 points where it's going to equal 0. These are my critical points. And I'm probably, just to be safe, I get into these formal ones. So I would go ahead and do the whole interval and say, okay, interval starts at 0 and it goes to pi over 3. Then from pi over 3, we're going to go from pi over 3 to what? To 5 pi over 3. And then from 5 pi over 3, we are going to go to 2 pi. So we do one trip around that unit circle, divvy these into certain categories here. So we got this. So the hard part, this one's not hard, or it is hard. It's sometimes thinking of a test point, in this case with trig functions. Once we have a test point, we're going to take the derivative there, and then we're going to come up with some kind of conclusion. In this case, we want to know, is it increasing or decreasing? So I am going back to that formal sign chart. I just think it organizes so nicely, and you can see what's going on. So all right, so sometimes it's hard to think of these test values. So what's between 0 and pi over 3? Well, something like pi over 6 would work. And if you like to think about it in degrees more, you can think of pi over 3 60 degrees. That's 30 degrees. But there's my test value, something in there. How about something between, we've got 60 degrees, and that's, I mean, if I look at the unit circle, anything over here will work. I'm going to pick pi. I think that's a nice friendly one to work with is pi, but anything in there will work. And then now this one could be tricky here. What's going to be wedged in there? Maybe like 11 pi over 6 will be wedged in there between 5 pi over 3 in there. So that's kind of the test values are kind of tricky there. But plugging them in is pretty cool. If I plug in pi over 6 into the derivative, so back to that derivative. So let's do that. We've got this pi over 6 idea, and my derivative was 1/2 minus the cosine of pi over 6. So what is that? The cosine of pi over 6 is going to be radical 3 over 2. So I'm looking at 1/2 minus that. So this is not real friendly. That's kind of a bummer. That's a rough looking number there. Without a calculator, you may be hurting a little bit here. But radical 3 is basically, is it bigger than 1? If it's bigger than 1, it's going to be a negative on top, and it is bigger than 1. So this is a negative number here because the top of that's negative. I got some doozies here. So the derivative of pi over 6 is actually less than 0, so it's negative. So what does that mean? It means this is decreasing. So here is a decreasing function on this interval. Awesome. Woo, I like this. Now let's put in the derivative. Let's put pi in there. I hope pi works out a little better. It's going to be 1/2 minus the cosine of pi. Well, what's the cosine of pi? Cosine of pi is out here. It's negative 1, 0. So we're going to say it's 1/2 minus negative 1. All right, this is something I can get into here. We got this negative is a positive, so it's 1.5 or 3/2, and it's positive. So we're going to say, hey, the derivative at pi is 3/2, which is positive. So this is an increasing function. And then will it go back down? I'm guessing it'll go back down. Let's prove it though. So we've got, what is this? We've got the derivative of 11. I keep writing pi. We got the derivative of 11 pi. It's hard to write 11 pi and not put pi. Put this in here. So we got 1/2 minus the cosine of 11 pi over 6. Well, 11 pi over 6 is going to be 1/2 minus just the cosine is the same thing. It's going to be the radical 3 over 2. It's the same thing, isn't it? So we've got this same dilemma where it's negative. So the derivative of 11 pi over 6 is less than 0, so it is decreasing. So all that work, but I have my justifications are there because, boom, I've got this right here is showing that it's decreasing. This is the key to the justification. You're actually showing that, then you write the conclusion from it. Now, I didn't have to do any max or mins. If I want to justify, we do have some max. It goes decreasing, increasing, decreasing. So I have a minimum and a maximum. You actually have to write that sentence if you're going to justify max and mins. But if you're just showing decreasing, increasing, just plug it in derivative, see what you get. Whew, this is great. This is good stuff. This is a big section right here. Let's wrap it up here. Here's the finale. What if I just give you a graph of the derivative, so none of that algebra stuff, and you just tell me what's happening? Where are my max and mins? So same thing. Locate all the critical points, and then we're going to see do we have any relative mins or max. So this is the derivative. Where are the critical points? Well, it's where it equals 0. So this is the start. I'm going to tell you on this one, there are 3 critical points. Critical points are -3, 1, and 3. So now I have to figure out, well, what's going on? Well, if you look to the left of this, what is the derivative? It's a positive derivative, so the function's increasing. There's a negative derivative, so what is this? Increasing function to a decreasing function is definitely going to be a max. So at -3, we have a max. How about at 1? From on the left side, it's negative, and it can be all over here, but it's right by it. Here we go, negative to a positive. If I go from a negative function to a positive function, that is a minimum. So 1 is a minimum. And if I look at number 3, it goes from positive to negative. So we just said positive, negative is the max. Now this is not enough. I want you to justify this. So I want you to go back, because I want you to get in the habit of always justifying. So you're going to have to go back and say, hey, there is a what? There is a relative maximum. Where is it at? It's at -3. And why is it there? Because the derivative changes from positive to negative. Holy cow. Isn't that awesome? Let's take that same sentence. I'm just going to copy it. Unfortunately, you have to do handwriting on this. And I've got 2 more critical points. So what is the next one? The next one is not a maximum, it's a minimum. And where is that happening? It's at 1. So first I figure out what it is, and then I do the write-up. So why is it a minimum? It's going from a negative to a positive. Boom, positive. Excellent. And then the last one was back to a maximum, not at -3, but it's at 3. So I can just say, hey, it's a maximum. Why? Because it changes from a positive to a negative. So if you want to justify these, what you're going to want to do, because it's going to be on the master check, you got to write that whole thing out. Why are you getting this here? Because you're changing signs. So whether you're looking at a table, a graph, or the actual equation, you have to show, you have to write this out to justify it. Awesome. So there's one more graph. I'm going to say pause it. You try it. See if you get these full sentences right up, and then I'm going to flash the answers up here on the screen in a second after you give it a whirl. All right, good luck. All right, here we go. So hopefully you identified the critical points at -2, 0, and 2. And then we had to write this sentence. And you're probably asking yourself, man, maybe you got to write this like, why do I got to write this sentence? Well, here's why. I mean, this is a perfect example to end on here. So the first one is it's a max, right? It's going from an increasing function to a decreasing function, so it's a max. The second one's a minimum. It was negative to a positive, so that is a minimum at 0. Check out what's happening here. It comes down and touches, so it has a critical point. Touches 0, and then goes back up. Well, guess what? It didn't change signs. It's positive, positive. This is something we're going to look at in the next section. So at x equals 2, there is no relative min or max because the derivative doesn't change signs. So this is why we check it. Just finding 0 or where it's undefined is not enough. You actually have to go and prove it by saying positive or negative. All right, that's the section. Good luck on the math check. Hope it goes well. Peace out.